Hello and welcome back. Today we are going to continue and actually finish up Chapter 10, Sequences and Probability, by finishing up Section 10.6 on counting. Yes, that's right. This is our final video of our final lesson of our final chapter of the year. Congratulations. All right, let's do a quick review problem here to start. Let's say my neighbor here has a lock on their door and they've got a 4-digit combo. And I want to break into their house, let's say. How many different combos are possible? Well, if you think about the fact that there's a 4-digit combo, you have to decide whether their order matters, and yes, for a combination, order matters. And then you have to decide whether or not there are going to be repeats are allowed, and in a 4-digit combination like this, repeats are allowed, so this is not a permutation and it's not a combination. You can just use the counting principle. There are 10 options for the first digit, 10 options for the second, 10 options for the third, 10 options for the fourth, which would be 10,000 different possible lock combinations. Let's say I call my friend, though, that works for the crime scene investigators, CSI. They use their magical blue fingerprint detecting light, and I can tell there are fingerprints on these 4 buttons, 1, 2, 9, and 0, which means those are the buttons that they press when they get into their house to use their combo. Now, how many 4-digit combinations can we narrow it down to? Well, one weird thing about this situation is you might think we've narrowed it down to 4 times 4 times 4 times 4. But actually, we've narrowed it down more than that. Because there are 4 different numbers that are used, I know I need to use each number once, which means I know there are not repeats in this situation right now. So I can use the counting principle and do 4 times 3 times 2 times 1, which is 4 factorial. That's 24. That is also the same as 4p4. All right, now we're going to start looking at some new types of problems today. So let's say I have 4 Scrabble tiles, these 4 right here. I want to know how many words that I could make with these 4 tiles. Now I'm going to define a word as any 4-letter string of letters. So these 4 letters in any order will count as a word. So all you need to do is do 4 times 3 times 2 times 1, just like the last example. So there should be 24, and ta-da, here they are. There are all 24 words. You'll notice I've got a few of them circled. That's because those are the ones that are actually words in the dictionary. So that's fun. But there are 24 different things I'll call words. Now, let's say that I have these 4 instead. Notice the difference here is that instead of N-A-W-E, I have N-E-W-E. Notice I have the letter E 2 different times. So here's what I'd like, how we're going to think about this. I'm going to start with my old list that had the letter A. I'm going to take out all the A's because I no longer had the letter A, and I'm going to replace it with the letter E. Ta-da! And now here's my new list. However, you will notice that some of these words are actually repeats. Like, look at those 2. That's the same thing, right? Because if you change the order of those 2 E's, like the E's are the same letter and those 2 are the same word, so then you have to get rid of any repeats. And if you count up how many are left, you will find these 12 words remain. All right? So basically, when I have, 2 things that are the same, I end up with half as many words. What happens when there are 3 things that are the same? So what happens in this? Now, instead of using that same thing where I replace, a W with an E, I'm just going to say, okay, it's pretty easy to just list these. Just put the N in different spaces and everything else is an E, and you just get these 4 words. So when you have 3 repeats, you have, 4. That would be a 1/6 of what we started with. Now, there is a relationship here between these totals. We had 24, then we had 12, then we had 4. So it was half as many as the original one, and then it was a 1/6 as many as the original one. So this is 24 divided by 1, this is 24 divided by 2, and this was 24 divided by 6. Well, it turns out that 6 you can think of as 3 factorial because there were 3 things being repeated. In this one, that 2 is 2 factorial because there were 2 things being repeated. So over here on the left, those are the formulas when you have items that are repeated or identical. And this leads us to a new type of counting rule called a distinguishable permutation. Now, if we're going to do a number of permutations with n objects of which p are alike, that means p of them are the same or identical. But you could also have other repeats. You could have some other thing where q of those are the same. Like if I had, a few s's and a few n's, I might have multiple things being repeated. Well, the formula is n factorial, that's all the total number of objects, over, and then every number that's, every item that's repeated just gets another, p factorial on the bottom, or another thing that's repeated gets a q factorial on the bottom, and you can have as many of these on the bottom as you need for as many things that are repeated. For example, how many 11-letter, again, quote-unquote, words could be made from the letters in the word Mississippi? So Mississippi has 11 letters, so I start with 11 factorial. But then you can see there's a lot of things being repeated. You can see the letter I appears 1, 2, 3, 4 times, so because the letter I appears 4 times, I put a 4 factorial on the bottom. Then the letter S appears 1, 2, 3, 4 times, so because of the letter S, I get another times 4 factorial on the bottom. The letter P is repeated twice, so I also do a times 2 factorial on the bottom. Okay, and when you type this into your calculator, be careful. You should put the entire denominator in parentheses, and just a reminder where that factorial button is. It's under Math, and then Probability. And then you can see that's what we did the last lesson, NPR and NCR. Here's option 4 is where you find that factorial operation on your calculator. You can type that all in and you get 34,650 different words that can be made of these 11 letters. Let's take a look at another one. Find the number of ways of placing 15 cubes in a row if 4 of the cubes are red, 3 are yellow, 6 are black, and 2 are blue. Hopefully you can kind of tell how simple this is once you know the formula. On the top is the total number of items, 15 factorial. Since there are 4 red, that's a 4 factorial. 3 yellow, that's a times 3 factorial. 6 black means we add a times 6 factorial. 2 blue means we add a times 2 factorial. And again, when you type it in, make sure you're typing in your denominator in parentheses. And you should get 6,306,300. All right. So that's distinguishable permutations. We're now going to go on to a new type of problem here. So let's say 6 students are about to hop on one of these merry-go-rounds. I don't know if you've had experience with those growing up on the playground, but there's 6 people about to hop on. How many riding arrangements are possible? Now, if you think about this, there are 6 spots on the merry-go-round, so you might just think, well, it's 6 factorial. But here's the thing about this object. It's a circle and it spins. And here's what that means. That means all these arrangements here are actually the same because this thing spins. So you'll notice, it goes from, going clockwise, it goes 1, 2, 3, 4, 5, 6. And this one goes 6, 1, 2, 3, 4, 5. And this one goes 5, 6, 1, 2, 3, 4. Notice these are all the same because here person 1's between person 6 and 2. And so, and here, and here, and here, and here. And if you take this thing and spin it, or think about a different starting spot on this, all of these are actually the same. Now, if I did 6 factorial, that would actually count these as different arrangements. But I don't want to count these as different arrangements. So you can see that I want all of these to just be counted once, which means you can see there are 1, 2, 3, 4, 5, 6 ways to rearrange, this single arrangement, which means I'm going to start with 6 factorial, but all I need to do is do a 1/6 of 6 factorial. So I just do 6 factorial divided by 6, which, if you write it out, that 6 will cancel with that, and you're left with 5 factorial, which is 120. So if you have a circular permutation, so you want to put n objects in a circle, then the number of permutations is n factorial over n, which you can simplify to n minus 1 factorial. So you could use either version there. They both would count the number of circular permutations. All right, I don't mean to bum you out here, but unfortunately, prom didn't happen, but we're going to have our own little mini prom here and talk about the best song to dance to. That's right, Party in the USA by Miley Cyrus. So let's imagine yourself at prom. You find yourself on the dance floor. Your favorite song comes on. Yes, it is Party in the USA. Oh no, you forgot how to dance. Quick, stand in a circle with your 8 friends and shuffle back and forth awkwardly. And how many ways can the 9 of you stand in a circle? So all you have to do is use this formula here. And that would be 9 factorial divided by 9, which is 8 factorial. So there are 40,320 ways that 9 people could stand in a circle. What's that? What's that I hear? What's coming up next? That's right, it's the Cupid Shuffle. Time to line up. So you and your 8 friends need to get into a line. How many ways could you line up? Well, that's just 9 factorial ways to get into a line. So that's 362,880. All right, one other thing I want to mention about a circular permutation is take a look at this example. So there's a CD changer that has a tray of that you put 4 CDs on. The arrow indicates which CD will be played. So you can see that they physically are arranged in a circle. How many ways can the CDs be arranged? Now this is actually different than the merry-go-round and the dancing in a circle because one of the positions in this circle is actually different than the rest. You can see that in each one of these, so even goes A, B, C, D, and you can see A, B, C, D, and A, B, C, D, and A, B, C, D. It's just, rotated. You can see that there's a different CD being played in each arrangement. So there are actually 4 factorial different arrangements, not 4 minus 1 factorial. So if there is a fixed reference point on the circle, so even if it's shaped like a circle, but one of the spots is different, well, then it can be treated as a linear permutations. So even if it looks like a circle, if one of the spots is different than the rest, then you can treat it as a linear permutation. So let's say you're at a restaurant and you've got 11 bowls of food that are placed on a circular revolving tray in the center of the table called a Lazy Susan. Now, is this arrangement linear or circular? So you have to think about, okay, this is a circle, it can be rotated. Are any of the positions on the circular tray different? And I would say no. So I would call this a circular permutation. So that's often the question you have to ask yourself first when you've got something arranged in a circle. Is any position different? Can I treat it as a circular permutation or should I treat it as a linear? Then once you know that, it's easy to use the formula and say, okay, 11 minus 1 is 10, so 10 factorial, use your calculator, that's 3,628,800. Well, that's it for me today, and I guess that's it for me for the year. Hope you had fun. See you later. Bye.